Welcome, everyone. Whoa. To Synthesis 1, we have 3 very exciting papers for you today. And our first paper is on inductive synthesis or synthesis from examples of recursive programs, and it will be presented by Woosuk Lee.
Thanks. Can you hear me? Okay. I'm Woosuk Lee from Hangyeol University in South Korea, and I'm going to talk about synthesizing recursive functional programs from input-output examples. This is a joint talk with my student, Hangyeol Cho. Let me first explain the form of synthesis problems we target. Given custom data types, and a type signature of the target recursive function along with a set of input-output examples, and a library of external operators that may be used by a solution program, we want to synthesize a recursive solution function satisfying the input-output examples. In this example, the given data type and a library are natural numbers and the addition operator over natural numbers, and the solution function doubles a given natural number. I will use this example problem throughout this talk. The synthesis of recursive programs has a long history. Since the 1970s, there have been various approaches and interesting applications proposed, such as end-user programming, invariant inference, automatic refactoring, and so on. In general, synthesis typically comes in 2 flavors, top-down and bottom-up. In top-down synthesis, searching for the unknown body of the target function f, we start with an initial empty partial program and gradually fill in program holes. For example, the initial hole may be filled with parameter x or plus, and left one may be filled with 3, and right one may be filled with another plus, and so on. During such an exhaustive search, any infeasible partial programs that can never satisfy the specification can be pruned away. Such pruning methods often require domain-specific reasoning. On the other hand, in bottom-up synthesis, we build increasingly large full programs from smaller ones. Starting from the smallest programs, such as 0x1, we can compose them together to build the larger ones until a solution is found. We can prune the search space just by evaluating the programs. For example, to find a single solution, we do not have to maintain both 0 plus x and x because their evaluation results are equivalent with each other for the given input examples. Because they behave in the same way, we can discard one of them. The major challenge in recursive program synthesis is recursion, which invalidates typical pruning methods in both top-down and bottom-up synthesis. In top-down synthesis, for example, suppose we have generated this partial program candidate during the search, which is actually infeasible because no matter how we fill in the program holes, we can never satisfy the spec. To prune such a candidate, we should be able to approximate all possible behaviors of each completion, which is not straightforward because there is a recursive call to the target function f, which is under construction. In bottom-up synthesis, to remove any redundant candidates, we should evaluate them. However, if a candidate program contains a recursive call, then we cannot evaluate because the target function is not defined yet. There have been various approaches to deal with recursion in both top-down and bottom-up synthesis. However, they have their own limitations. They suffer from scalability issues, or they impose strong restrictions on the user specification. We propose a novel general method for synthesizing recursive functional programs. And we propose 2 techniques we named block-based pruning and library sampling for handling recursion and library without any complex domain-specific reasoning, respectively. And our method guarantees to find a solution if it ever exists. And we implemented a tool we named Trio, and it outperforms the state of the art. And the tool is public. Next, I will explain our key idea using the example of synthesizing the double function I mentioned earlier. Given these three input-output examples, we want to synthesize this target function. And from now on, I will use 0, 1, 2, and so on as a shorthand for natural numbers. Our key idea is to carry out synthesis in two phases. In the first phase, for each input-output example, we synthesize all possible non-recursive and conditional-free simple expressions satisfying the example. We call such simple expressions blocks. And then, in the next phase, we perform a top-down search over the space of recursive functional programs, and we prune any candidates inconsistent with the blocks obtained in the previous step. I will explain the meaning of inconsistent in a moment. Here are examples of blocks synthesized for each I/O example in the first phase. Any non-recursive and conditional-free simple expressions that evaluate to the desired output 0 when the input is 0 are blocks for the first I/O example. Similarly, any simple expressions that evaluate to 2 and 4 are blocks for the second and third example, respectively. Typically, there are an enormous number of blocks we can synthesize. Suppose we could synthesize all such blocks. In the next phase, we perform a top-down search over the space of functional programs. Suppose we have generated this partial program candidate during the search and want to check feasibility of it. If it is infeasible, we can prune the search space. I will show you how we can prune this candidate using the blocks. For pruning, we perform partial evaluation using each I/O example of this candidate program. The result of a partial evaluation will be a partial non-recursive conditional-free expression, possibly with missing holes in it. For example, after one step of a partial evaluation, the parameter x could be replaced by z here because the input example is 0. Because the scrutiny has been fixed, we can take the first branch. After another step, we obtain this partial expression. Then we search for blocks that can be matched with this partial expression by properly filling in the hole. 0 plus 0 or 0 plus x are such blocks that can be matched. The meaning of this is there exists a completion of the partial program candidate satisfying the first I/O example. Similarly, for the second I/O example, using that example, we perform partial evaluation of the candidate program. After one step, x can be replaced by s of z because the input example is 1. And then the second branch could be taken. And after another step of a partial evaluation, we have this partial expression. Whenever we have a recursive call, the body of the candidate program is substituted into every position of a recursive call. So after aligning the body of the candidate program, we obtain this partial expression, and then the first branch can be taken here. As a result, we obtain this partial expression. Then we search for blocks that can be matched with this partial expression by properly filling in the holes. However, there is no such blocks that can be matched because any completions of this partial expression will evaluate to numbers greater than 2, which is the desired output. The meaning of this is there is no completion of this partial program candidate satisfying the second I/O example. So we can safely discard this candidate because there is no hope for satisfying the second I/O example. We call this pruning method block-based pruning. To realize this key idea, we had to address two key challenges. First, in the first phase, to make the pruning correct, we must not miss any blocks satisfying the examples. However, there are an enormous number of blocks we can synthesize, so we should be able to synthesize all of them very efficiently. In the second phase, we check consistency of each partial program candidate with respect to the blocks obtained in the first phase. And the blocks are in an enormous amount, so checking consistency should be done efficiently as well. To address the first challenge, we combine top-down and bottom-up synthesis by adapting a previous bidirectional search technique into our setting. And with an efficient data structure called version space, which I will explain in a moment, we can synthesize over 1 billion blocks within 0.1 second. Addressing the first challenge. To address the second challenge, we use an efficient data structure called version space. A version space is a graph where each node represents a set of expressions. Each leaf node here represents a single expression, and they are composed into larger sets. A union node marked with U represents a union of all its children, and a join node marked with bow tie applies a function symbol to every possible combination of expressions represented by its children. This graph represents this set of expressions, and it can be further simplified by removing any duplicate nodes. A version space can represent exponentially many expressions in a compact manner, so that we can compactly represent a large set of blocks, addressing the second challenge. Here's an overview of our system we named Trio. The system takes a specification, including a library of usable functions, and an integer n as input. And three modules interact with each other until a solution is found. The bottom-up enumerator generates a set of components whose size is less than n, and a set of inverse maps of library functions. I will explain what they are in a moment. Given these two ingredients, block generator generates a set of blocks satisfying each I/O example. Given these blocks, candidate generator explores the space of recursive programs in a top-down manner, pruning the space using the blocks. If a solution cannot be found, that means we need more components. The integer n is increased, and bottom enumerator now additionally generates larger components, and the entire process is repeated until a solution is found. I will explain each module in more detail. First, the bottom-up enumerator generates a set of components which are sub-expressions that may be used by a solution. It generates components whose size is less than or equal to integer n, which will be increased again and again until a solution is found. Suppose we have obtained this following component set C. It additionally generates a set of inverse maps. An inverse map is a function from output to input of a library function. For example, the inverse map for the addition operator is shown here. Given an output, it returns a set of inputs that can produce the output. Such an inverse map can be obtained from input-output samples collected from evaluation of a library function. And those inverse maps will be used for reasoning involving the library functions in the following synthesis phases. The problem here is there may be infinitely many input-output samples that can be collected. So we limit the set of inputs that can be used for sampling to be a set of finite values, not greater than the maximum input example. For example, if the maximum input example is 2, then we only use 2 pools comprising 0, 1, 2 for sampling. The reason for doing so is we target structurally recursive programs where arguments of recursive calls are structurally decreasing to guarantee termination of synthesized programs, and input to a target function often flow to library functions called inside of it. Next, the block generator. It generates a set of blocks satisfying each I/O example. Each set of blocks is represented by a version space. For example, here's a process of constructing the version space of blocks for the second I/O example. Given this component set C, the initial version space only contains a single union node because we will generate multiple blocks. We first search for component satisfying this example, and such components will be added into the version space. Because 2 and x plus 1 evaluate to the desired output 2 when the given input is 1, they are added into the version space as leaf nodes. We keep searching for blocks of other kinds as well. Suppose we search for blocks of form E1 plus E2, where E1 and E2 are blocks. At this point, we use the inverse map for the addition operator. It returns 3 pairs of inputs that can produce the desired output. So we create 3 join nodes for these input pairs. Each join node has 2 children, one for each element of a pair. For example, because 0, 2 can produce 2, we have a join node whose left child is for expressions generating 0 for the given input 1, and the right child for generating 2. We keep searching for blocks for newly generated I/O example. We search for components satisfying this example, and 0 is such a component, so it is added into the version space. And then we search for blocks of form E1 plus E2. Using the inverse map, we identify a single input pair that can produce the desired output. So we create a join node for this input pair. We keep searching for blocks for other unprocessed I/O examples and keep constructing the version space. And during this process, any duplicate nodes are removed to save the space for the version space. Next, the candidate generator. It searches for a recursive solution program in the space of recursive programs. And during the search, suppose we have generated this partial program as a candidate and want to check feasibility of it. As I mentioned earlier, using each I/O example, we perform partial evaluation of the candidate. For example, for the second I/O example, after multiple steps of partial evaluation, we obtain this partial expression from the candidate program. And then we check if this partial expression can be matched with any blocks represented by the version space constructed before. Because the top-level function symbol is addition, we identify a join node with addition first, and we check if 0 can be matched with a block represented by its left child and find 0, and a whole can be matched with any expression. So the right child node is determined to be its counterpart. Because this partial expression can be matched with some blocks in the version space, we conclude that the partial program candidate can satisfy the second I/O example in the future. For the other remaining I/O examples, we do a similar reasoning process. A problem is there may be infinitely satisfying blocks for each I/O example, so the version space may be infinitely large. For termination of the block generation process, we limit the height of a version space. Because of this, blocks of a solution may not be generated, and the block-based pruning may be unsound because partial programs leading to a solution may be pruned by mistake due to the lack of blocks. However, despite this pruning unsoundness, we never miss a solution. Because if valid partial programs are pruned and we can't find a solution, we repeat the process after adding larger components because of this feedback loop. The more components we have, the more blocks we can synthesize. So eventually, the valid partial programs will not be pruned because blocks necessary not to prune them will be there. To evaluate our approach, we collected 60 functional programs from the prior benchmark suite and OCaml tutorial. And we use two kinds of specs, I/O examples and reference implementations. We compare our tool with Smith, the best top-down synthesizer, Burst, the best bottom-up synthesizer, with 2-minute timeout per problem. Each plot shows the number of problems solved within a certain amount of cumulative time by each solver. Blue lines represent the performance of our tool trio, and the closer to x-axis, the better. In conclusion, our tool outperforms the other baseline tools in all kinds of specs. In particular, our tool could solve all but just one problem for the I/O spec problem. We also performed the ablation study. In conclusion, Trio performs better using the two techniques we proposed, block-based pruning and library sampling, than without any techniques enabled. You can find out more details in our paper. Thank you for your attention.
Questions? Okay.
Hi, thanks so much. I think it's very impressive how you combined the top-down and bottom-up synthesis. Well, I was wondering, when generating the blocks, it seems like you only use some top-level expressions to generate the blocks. But when you perform a pattern match, for example, you might introduce new variables. Are those considered in the generation of blocks?
Generation of what? Sorry? Generation of...
So during the block generation, there's now you only use the variable x, but maybe you pattern match at some point during the top-down synthesis and introduce a variable y. Can that be used in the generation of blocks as well? Will it be introduced later on?
Oh, sorry, I couldn't get
The question is about local variables. Like inside the pattern match, you have a local variables, right?
Yeah.
So do they appear in the blocks?
Why do we need to synthesize?
Why don't you need them in the blocks, right? Why don't you need to use them in the bottom-up phase? Is that?
So you are asking why do we need the parameter in the block generation process?
Can you hold your mic a bit closer to you because I cannot even hear you from here.
So, I'm very
Can you answer again? Because
No, I
could you
couldn't
hear
hear
it?
it, no.
Yeah. We could not hear you. Can you say it again with your mic closer to your face?
Oh, I don't get it. Mic is not going well. Maybe we can talk offline.
Yes, that's okay.
Yeah.
So you mentioned in one of your examples that you are unrolling the recursive calls.
Yes.
But in that specific case, it was 3 plus some recursive calls. So you could already eliminate it at that point. So do you ever do that, or do you just, is that not particularly helpful?
This one?
Right, so even on the left, you've got 3 plus f of z plus blank. If you treated f of z itself as a variable, you're still not going to be able to synthesize that because that's already greater than 2. So do you prune there as well, or do you only prune after you've fully expanded it out?
I'll say that again. So, sorry.
So, 3 plus f of z plus
Yeah.
whole.
Yeah.
Already at that point, you don't have a solution, right? Because that's already greater than 2. So if you don't expand it, it's already greater than 2. Do you ever prune there, or do you not prune there at all?
So, maybe we can talk offline.
I think we probably out of time. I'm sorry, we're out of time. Let's take the other questions offline. Let's thank Woosuk again. The next speaker should sit down.